Alright, so in this video I'm going to be explaining another important article with this title, Inferring Latent Domains for Unsupervised Deep Domain Adaptation. Because sometimes your domains are not explicitly given, so we need to discover them and put them under this latent discovery structure. So this paper in 2021, unsupervised domain adaptation refers to the problem of learning a model in a target domain where labeled data are not available by leveraging information from annotated data in a source domain. Most deep unsupervised domain adaptation approaches operate in a single source, single target scenario, where they assume that the source and target samples arise from a single distribution. However, in practice, most datasets can be regarded as mixtures of multiple domains. In these cases, exploiting traditional single source, single target methods for learning classification models may lead to poor results. Furthermore, it is often difficult to provide the domain labels for all data points. Latent domains should be automatically discovered. This paper introduces a novel deep architecture which addresses the problem of unsupervised domain adaptation by automatically discovering latent domains in visual datasets and exploiting this information to learn robust target classifiers. Specifically, our architecture is based on two main components: the side branch that automatically computes the assignment of each sample to its latent domain, and novel layers that exploit domain membership information to appropriately align the distribution of the CNN internal feature representations to a reference distribution. You see the idea behind the proposed framework, that here we have this domain discovery layer because sometimes we don't know explicitly, and then we have domain alignment. So we introduce a novel deep architecture given a set of images automatically discover multiple latent domains and use this information to align the distributions of the internal CNN feature representations of sources and target domains for the purpose of domain adaptation. In this way, more accurate target classifiers can be learned. So our goal is to learn a predictor that is able to classify data from target domain. The major difficulties that this problem poses and that we have to deal with are the distributions of source and target domains can be drastically different, making it hard to apply a classifier learned on one domain to the others. We lack direct observation of target labels, and the assignment of each source and target sample points to its domain is unknown. Because sometimes the domains are not explicitly given, so we should discover them using that latent variable. So or there are known for a very limited number of source sample points. Some sample points we know which domain. For example, this sample point is domain 1. This sample point is domain 6. But the rest of the sample point, we don't have any category. We don't know which of them. No, we don't know which of them. For example, it could be 1. This could be assigned to 1, but it could assign to anything else. We don't know that. The annotation is just for those that are given. So So several previous works have tackled the related problem of domain adaptation in the context of deep neural networks. In particular, some recent works have demonstrated a simple yet effective approach based on the replacement of the standard these batch normalization layers with specific domain alignment layers. I had an article about this idea. It's very interesting. So they have some layers inside that does this very interesting. And so domain adaptation layers are motivated by observation that in general activations within a neural network follow domain-dependent distributions. So this QD is the distribution of activation for a given feature channel and domain D. So the domain adaptation layer can be normalized according to this. So we have just the mean and variance of the input distribution. So we define the global input distribution as just a linear combination of these domains, where pi, the coefficient, is the probability of sampling from domain D, because there is a distribution for each domain. There is a distribution that we can sample from that. And then Q, the conditional one, is the condition probability of xi belonging to domain D given x sub I. But the interesting part is here. We obtain a new set of empirical estimates of the mixture parameters, which we denote by mu hat and sigma hat. These parameters are used to normalize the layer's input. And then the domain prediction branch is implemented as a minimal set of layers followed by two softmax operations. So you see the architecture, which is applied to AlexNet on the left, and on the right you see this domain adaptation layer that we put here in the middle between any fully connected layers of the AlexNet. We put these interesting domain adaptation layers. Look, we know the mean and the variance of the domain, and we know how to normalize them, and so the output is based on your weight and x sub I. And the loss is sum of loss term penalizes based on the classification, and this accounts for domain classification task. But the classification, final classification task is just a sum of f and h, and this term is just the entropy of the classification distribution, average overall unlabeled target examples, and it is scaled by this positive hyperparameter. But the first term is just a classification branch of the network of a source sample. And here we have domain loss akin to classification loss. A domain loss presents a component exploiting the supervision deriving from the known domain labels, and a component exploiting the domain classification distribution on all sample points lacking supervision. However, the domain loss has, in addition, a term that tries to balance the distribution of sample points across domains in order to avoid predictions to collapse into a trivial solution, such as constant assignment to a single domain. Accordingly, the loss takes the following form. So this f theta sub d sub s is just domain prediction branch for the source. And of course, this one is domain prediction for target, domain prediction for target. But f bar here is just the average of them, average of predictions. So the first term in 6, the first term, enforces the correct domain prediction on the sample points with known domain, and it is scaled by parameter lambda d. Since the classification branch has a dependence on domain prediction branch via the domain adaptation layers, the network learns to predict domain assignment probabilities that result in a low classification loss. In other words, the network is free to predict domain memberships that do not necessarily reflect the real ones, as long as this helps improving its classification performance. So on digits 5 dataset, the comparison of different single source and multi-source domain adaptation models, for example, for Street View, for MNIST, and also comparison of different models in multi-source. MNIST M are taken as source and UPS as target. So we are going from this source to this UPS, which is our target. You see different methods, different models, and the paper has this accuracy. So for example, you can take photo as a target, or a cartoon as a target, or art sketch. Any of these sources could be source domain, could also be, you could either choose, for example, 3 of them you put as source domains, the other one, the rest of that are the target domains. And you see the distribution of alignments produced by the domain prediction in all possible multi-target settings. So PAX is, P is photo, A is art, C is cartoon, and S is sketch. PAX dataset, which is very good for multi-source domain adaptation and even multi-source domain generalization if you consider your target to be unseen. Another interesting dataset is Office Caltech dataset. The first row, we indicate source on the top, and the target domains are in the bottom.